Hey guys, so this is my brief video on dynamics, um, which is a very essential part of physics and pretty basic. So I'm just going to cover it like really briefly. You probably won't even need this video. It's just in case you do, you need a little refresher. Um, so here we go. So if I've got a function x of t, right, that is my position function. And this is really the big function that we're going to be dealing with in regular physics, not in quantum physics. But this is our position function. X is where we are, like along the x-axis is a function of t, time. Now we can have a vector x, or really we usually call this delta x, and this is called our displacement vector. And that is, it has, and it can be a function of time as well, right? And this is it is how much you've moved. Displacement is how much you've moved, right? With respect, not with respect, in addition to the direction in which you move. So it's a vector, right? As you can see with our direct vector hat. Now we have what is now called velocity, which is the derivative of our displacement vector with respect to time, right? And this is equal to velocity, which is a vector, right? Speed is the magnitude of this vector, the speed. And then we have one more quantity. These are called our kinematic quantities, and it is acceleration. And we can define acceleration, right? So velocity is the rate of change of position. It's in this derivative. Hopefully you're familiar with it, right? dv, derivative of velocity with respect to time, is equal to acceleration, right? Which is equal to the second derivative, d squared x, second derivative of displacement, divided by dt squared. And again, hopefully you're familiar with velocity and acceleration. Khan Academy will have videos on it. In their physics section, their basic physics section, it is not too difficult. Right, so these are kinematic quantities. We've got a few more quantities that we're going to be dealing with. So I'm going to erase this. This is like the really basic stuff. Get a little bit more involved into this when we're dealing with things such as momentum. Right? So momentum, which is represented by lowercase p, momentum is equal to the mass of an object times its velocity, right? And then we can define force. Force is, and this is Newton's second law, in its actual presented form. Most people will see it as mass times acceleration. I'll show you where that comes from. So dp by dt, right? Force is the time derivative of momentum. Now, considering momentum is mass times velocity, if mass is constant, which it usually is, although, like, for example, in rocket science, the rocket's going to repel itself by losing mass. So actually, Newton's second law in the form F equals ma is not actually going to hold. Um, uh, this is the most general form, but usually when mass is constant, which we'll be dealing with for most of this course in quantum mechanics, not all of it, um, this is mass times the derivative of velocity with respect to time, right? Because you can take a constant out of the derivative, so mass times acceleration. Oftentimes you'll see it written like this: net force equals mass times acceleration, right? Or the net force is equal to the time derivative of momentum, right? Um, Qualitatively, this just means force, right, is what causes a change in, or what force is what causes a change in momentum, right? An object has a momentum mass times velocity, right? And it keeps on going that unless you have a force that decides that it's, well, a force that you apply to change the momentum of the object, right? Which accelerates which gives the object acceleration. Now, if you have like a force going one way and the same force going the other way, there's no net force, right? This is zero. There's no acceleration. Momentum is not going to change. So you need really a net force. So this law truly should have a net force with it. Hopefully this all makes sense. Finally, the last thing, and this is the one that some people may not be super familiar with. We can have, instead of x, we have the r vector. And the r vector is simply this. It is x times I hat plus y times j hat plus k, or plus z, sorry, z times k hat. And this is the three-dimensional version of displacement, right? It's the displacement in x times the x unit vector, displacement in y times the y unit vector, displacement in z times the z unit vector, right? K hat. And that just means it's just a way to generalize displacement to include movement in three dimensions, which is how our real world works, right? We can then have a velocity in three dimensions, and that velocity would be a three-dimensional vector. It would be the vx times I plus vy times j plus vz times k. Same thing with acceleration. Do that with momentum, with force. We can generalize all of this one-dimensional stuff into three dimensions, and this r vector is important, and that's what we're going to be calling it through this course. So that's really important. Other than that, hopefully, I mean, you guys have got this. This is pretty easy stuff. If you're not familiar with it, you can go on to Khan Academy. But I don't think I'm going to link it just because I'm guessing most people are not going to be needing this. Okay, I'll see you in the next video.